All right, so first, before we kind of jump into things, just take some housekeeping stuff. So that Connect assignment, I realized that if you looked on the Connect platform, it was showing up, and I tried to deploy it simultaneously for you in another section. And I realized, I think it was last Thursday, that it wasn't showing up. So I made sure I got it deployed, so it should have been up there Thursday and Friday. The link should have showed up to you. But because some of you might not have realized that, I know I can't mention the Connect assignment, but because it wasn't appearing on Canvas, I kind of pushed the due date. So originally it was the same as this first Excel assignment. I've noticed I kind of pushed it up until next Thursday, basically, kind of once I realized that Thursday, I gave you a whole other week in case you didn't realize it was there. All right. So the Excel assignment is due the 13th, which is what? Monday at the end of the day. And then the Connect assignment will be kind of that Thursday. I was going to make it Wednesday when we have class, but I figured making it that Thursday, if you have some last minute questions, will be available for office hours next Thursday. So those are kind of the two assignments. Also, before class today, I put this next Learn Smart. That's due when class begins next Wednesday. So this is up a little bit early. You don't have to by any means do this today or even tomorrow. You can kind of wait until next week. It's kind of like the other one's pretty easy, 5-10 minutes of just go through, kind of prime us for the next topic that we'll be talking about next week. That Connect assignment, I also put in the announcement, there's 2 questions, 11 and 12, that have a part B to them that I don't expect you to do. So, you can submit it, and then after the due date, I'll give everybody credit for that part B. So, you don't have to put an answer in there, even though it looks like you won't have all the points. If you don't do that, once the due date's passed, I'll go through and give everybody full credit for those part B on the questions. I believe it's 11 and 12. Here, I had it in the announcements. Yeah, 11 and 12. Okay. Other than that, I had a question. Someone asked me about where the YouTube stuff is. So the easiest way to find the YouTube page, you can go back in the syllabus, the first week of slides. I have the URL link. You can click on that. It'll send you to our sections playlist on YouTube. Probably the easiest way to just search Professor Lannis on YouTube. I'm the first name that comes up. I know I went over this week 1, but I'm getting alarmed that I had a question on it. So search Professor Lannis, first thing that pops up, and then just click on playlists and section, Econ 221, section 5, right? Or section 5. And all the videos for the class are there. So that includes the recordings of, me talking and kind of the stuff that's on the slides. Pre-class videos, there's an Excel video number 1 up there. It's kind of a, go back and see the example that we did in class, but all spliced together because it went across a couple of class periods. Other than that, is there any questions for me before we jump into the material for today? No? Okay. So we left off, talking about weighted means. Okay. So if we can do a weighted mean, which is where we have group data, we can't see the original underlying individual data, the best we can do is come up with a weighted mean. So if we can do a weighted mean, right, this measure of central tendency, we can also do this measure of, well, how much on average does the group data vary from this middle point, right? So we can do a weighted variance. It's going to look really similar to what we did with the weighted mean and what we did with just a regular variance, kind of combined into one. All right, so it's not like a brand new process, right? We're kind of combining 2 principles we know. So we have 2 equations for this. This is probably going to be the one that is the best way to, procedure how we're going to have to go ahead and solve these. But I want to make the connection between the 2. So we're doing the weighted mean. We had my summation sounds kind of bad there, but for each observation we went through, we took the weight for that group, multiplied it by the value for whatever X variable we were interested in for that group. We did that for every observation, then added them all up, and then divided by the sum of our weights. Well, another thing that this sum of the weights represents, and this will be a little bit clearer in one of the examples we go through today. But if I had a data set of every individual's income, right? That's the original data. It was in John Smith, his income, Joe Buck, his income. That name, Joe Buck's like an announcer, right? So anyways, but I don't know why that name came to me, but I could see every individual's income, but I only have the data grouped, right? So the weights or the frequencies in each one of those groups should add up to just the total number of people that were in that original data set that I can't see, right? Because every person was only counted once. They only belonged to one of these groups. And so the sum of my weights should be the number of observations that was in that original data set I can't see. The original data set that was then put into group data. So whether or not we want to think about this denominator as the sum of the weights or the total number of observations in that original data set, right? Usually we don't have this, but we've got the weights, so we can add those up. So the weighted variance is going to be really similar to the regular variance, right? In the sense that we go through each group, we take their value for the x variable and subtract the mean, right? What was that group's deviation from this middle point of the data, or from this mean? We'll take that deviation and square it. The only additional thing we have to do if it's a weighted variance is then multiply that deviation by the weight, okay? Because, you know, if one group deviates from the mean a lot, but it only represents 3 people, well, that shouldn't influence our variance near as much as if we have an observation that doesn't vary from that middle point very much, but it represents 3,000 people, right? So we had kind of this example from last class, and don't worry about this column for a second, where we had kind of, here I just took the male income data, and we had it broken down by race. We had the average income across these 4 different race groups, and then the number of individuals that each one of those averages represented, right? So kind of think about it this way. I think it was about 53,000 was the weighted mean that we found, right? So with that weighted mean from last Wednesday, 53,000, this point varies from it by quite a bit, and it represents a really large number of individuals. So we go through that first observation, take that 59,000, subtract the mean of 53,000, square that deviation. That's just what we're doing for the other variance. It's just now, once we have that deviation squared, we then multiply it by 73,000, or the weight for that group. So notice with this income data, these end up being like really, really large values. I would never give you an example like this on the exam or something to do by hand, because this is just, I mean, these, calculating these intermediate numbers is pretty wild, right? But it's because we have pretty big number of observations, right? Our weights are pretty large values. And when you're dealing with income, you very easily see deviations from the mean of being in the thousands as well, right? So notice that 53,000 mean, I mean, 38,000, 36,000, pretty far away from that, right? But notice, what's a good example of this? Here we go. So 59,000 is about 6,000 away from 53,000, right? 60,000 is a little bit further, right? About 7,000 away. So those deviations from the mean, right? They don't add the same amount to that numerator, because we need to take that deviation squared and still multiply it by the weight for those groups. So notice, even though this value is further from the mean, it represents a much smaller amount of people. So when we take that deviation squared and multiply it by the weight, this number is quite a bit smaller than this one, even though this observation, this group, was further from the mean, right? And that's because even though it was further from the mean, it shouldn't carry as much weight in that variance calculation. So it might be kind of hard to see, but right, there's actually like here's got 12 goes out a whole nother place, right? For that group where we had 73,000 people. So once we have that deviation squared multiplied by the weight, we then add all these up, right? That's going to be some god-awful large number. Once we have the sum of all those deviations squared times weight, the final step was we divide by the sum of the weights. So we add these up and then divide by the sum of our weights here, okay? If we do that, we get about 94,000. We'll work through one like individually. I'll show you, I think presented a little bit better in just a second, but I'm kind of showing you these slides because it was data we used from last class. And it might be good to try to reproduce these values, right? It might be a good exercise on your own if you're looking for an extra way to kind of study or make sure you're following the material. Try to reproduce these weighted variances, okay? I put the female data up there as well, and then the region, right? So this is just values. If you want to go back through and try to calculate the weighted variance and reproduce these values, might be some good additional practice. We're going to work through more in detail a weighted variance example right now. We're going to throw a couple more wrinkles in it, but at least we'll get to kind of piece it out and break it down a little more and kind of work it out. So let's say I've got a group data set that looks something like this. Numbers are a little smaller. It's going to be a little more manageable for us to think about this. Well, I've got frequencies, right, which seem like a pretty good variable to use as my weights, right? This group, this value represents 25 people, while the satisfaction rate of 36-38 only represents 4, right? So we're going to treat those frequencies as our weights. The problem is, what do I use for my X values? The variable I'm interested in here is this satisfaction rating. I think it was, I forget. There's some data set, like the satisfaction rating of some service, right? Like it might have been like a hotel or something like that, right? And people just ranked how satisfied they were. And they were all integer values. So there was 4 people that responded with either a 36, 37, or 38. 25 people responded to either 42, 43, or 44. So the data here is grouped by like into bins, kind of like what we did when we did those frequency distributions, right? Or what you should be doing for that first Excel assignment, okay? You're gonna have all these different bins. You're gonna say there's this many people or observations in this bin, this many observations in this one. But if that's all you could see is the frequency distribution data, and you couldn't see the original data set that it was built from, well, now you're gonna have to do a weighted mean and a weighted variance. I can't go and look at every individual's satisfaction rating response here. I can only see that 4 of those people in the original data set responded with a 36 through a 38. So what do you think we'll probably use for our X values here, right? If the satisfaction rating is what I'm interested in, but it's in bins, what would be a good thing to do?
Probably the average.
The average, or what we're gonna actually end up doing, close to the average, is actually using the median or the midpoint, right? So we'll use them, if we ever have data in the bins, group data in bins like this, we'll use the midpoint of the bins as our X value. But really, other than that, procedure, it's going to look exactly the same as what we were doing before. Okay? So if we want to do the weighted mean, before we go to the equations, if we're looking at this, just to kind of think about the concept of what we're doing, probably around where would you say the mean of this data set's going to be, the weighted mean? So this is where you got to be careful, right? You were actually looking at the frequency variable. The frequency is what we're going to be using as our weights, right? We're actually interested in what's the weighted mean of this satisfaction rating variable, okay? So if I'm looking at, this is the variable I want to find the weighted mean of, the frequencies are telling me the value of, using the midpoints, 43 is going to be weighted a lot, while the values of 49 and 37 really don't represent that many people, so they're not going to carry near as much weight in my calculation. So if instead I'm focusing on this weighted mean of my X variable, the satisfaction rating, about what do you think the weighted mean will be around? Yeah, 42, 43, probably somewhere else. There's a few more observations on this side, so maybe it gets pulled up a little bit, but you've got more observations that are further down at the bottom, so maybe that pulls the mean. It's kind of hard to say, but probably somewhere in the 40s for sure. Definitely not anything outside the range of 49 to 37, right? How could we have a weighted mean? It's still a measure of central tendency. How could that middle point be past, below the minimum value or above the maximum? That would make sense. So what we're going to do is rewrite our weighted mean equation just a little bit. It's really just notation differences. Notice here, instead of weights, well, my weights are the frequencies I have. That's really, that's kind of semantics, right? If I'm using my frequencies as the weights, do I really need to call them, write them differently? Probably not. But because we're using this midpoint, because this is really going to be a situation where we only see this type of data where we have to use the midpoint when we've got these frequency distributions, we always know in these situations, our weights will be frequencies, right? But it's the same kind of idea applies. And then instead of writing it as a variable X, right? Well, we just kind of notate, well, we're using the median or the midpoint of these bins as our X variable, right? Because we know that, we wish we could look at the original data and see every individual satisfaction rating response, but we can only see it in these bins. Okay? Other than that, it's pretty much the same thing here. And then we have the same thing kind of applying. If I add up the frequencies, remember for that frequency distribution, one check I told you could do in Excel was once you add up your frequencies, it should be the total number of observations in the original data set, right? Every individual should have been counted at only one time, right? Should only be in one of those bins. So when I add up those frequencies, it would count every single person one time, which would then give you the total number of observations in that original data set before you put it into this frequency distribution. So you can write this as a sum of the frequencies, or we can think about this as the total number of observations n in that original data that we can't see, right? All we have is the kind of data forced in the bins. Any questions on this before we keep moving? And this will be the one I'll end up showing you kind of a little more step-by-step how we calculate the weighted variance as well. Excuse me. So we can also do the same thing for the variance here. It's really just a weighted variance. I'm just using frequencies as my weights, and the X value, I have to use the midpoint or the median. Okay? Now, one thing that I have down here, just so we remember, kind of going back and kind of relating to things we talked about, if I only have sample data, let's say I'm doing a weighted variance for a sample, right? The satisfaction rating, which is a small subset of people who use the product. And so I only had sample data. But when calculating the variance, the same rules apply. Whether or not it's a variance or a weighted variance, I need to be dividing by n-1 for a sample instead of capital N, which was for a population data set. So I've got a sample variance. I'm actually, I'll move out of the way here in a second. All right, I'll have that same numerator, but another way to think about the denominator is I'm really going to be taking the sum of my frequencies, but because it's a sample, it's my sum of the frequencies minus 1. Well, the sum of the frequencies is just n, right? The original number of observations in that data set I can't see. So you can write it either way. More often than not, we're not going to be given this. We're not going to be given n. So we're actually procedurally going to have to add up those frequencies to get n. But then because it's sample data, I still have to subtract 1 there in the denominator. Okay. So let's look at an example of this. So the first thing I'll kind of walk through, doesn't really look anything different from what we were doing Wednesday with weighted means, is I'm going to go ahead and calculate my weighted mean. So the first thing I need to do, go through every observation, take the weight, which is now my frequencies, multiply it by that median of each kind of group or each bin, and then add them all up. So go with the first one, 37 is the midpoint. I'll subtract, don't subtract. That's the variance. What do you mean? So I'll take that value of 37, I'll multiply it by the weight or the frequency. 4 times 37 is 148, write that number down. For the next observation, next group, the midpoint is 40, multiply that by the weight or the frequency. 40 times 15 is 600, write that number down. Go ahead and do that for every single observation we have here. Once I've done that for every single bin or every group, add those products up, I get 2,795. And then finally, I divide by the total number of observations in that data that I can't see, which we said was the same as the sum of my weights or the sum of my frequencies. So if I add up my weights or add up my frequencies, I'll get 65. So that becomes my denominator. Okay. So we get a weighted mean of exactly 43. And these numbers were chosen for a reason. Yeah.
So when we're multiplying the satisfaction rating and the frequency, why don't we square them?
So we only square those deviations when we're doing the variance, right? So to get to the weighted variance, we first have to have the mean, right? So think about it this way. The reason why we were just multiplying across was what we're actually doing with weights is let's use this one. So we've got total, the sum of the frequency here is 65, right? So in this original data set, there was 65 individuals. That very lowest bin, so that midpoint of 37, only represents 4 of them. So really what we're doing is we're taking that value of 37 and we're actually weighting it by however many observations it represents out of the total, right? We would go through, the next one is what, 40. It represents 15 out of those 65 people, right? We could do it this way. A lot of people, I don't think this, I mean, maybe it does for some of you. this doesn't make as much sense, or procedure, it's just a little bit easier to make mistakes or harder to think of. But if this is how you want to think about it, that's really what you're doing. You're just taking these different values and you're saying, well, look, this only represents 4 out of 65. This represents 15. So we're going to use those as my weights. Well, if those are my weights, then the sum of my weights in the denominator will always just be 1, right? But if I rewrite this, right, everything's being divided by that sum of the weights, the sum of my frequencies. So I can, right, just write it like this, and then multiply the frequencies by those midpoints. It's not 40, is it? Oh yeah, it is. Sorry. So it's just different ways of thinking. I can't kind of like add things to your question, but did that kind of get at what we were asking, or not quite?
Yeah, and this, we're finding the average of this, right? You said?
Yes.
Okay.
Yep. Okay, this is just our weighted mean. Yeah. So we get a weighted mean of 43. Well, that was the first step in finding the weighted variance. We had to have the mean first. That's kind of why we switched from weighted variance back to weighted mean, because we had to have that first. So now that I have that weighted mean of 43, I can go through and find that numerator for my weighted variance equation, right? Take that deviation from the mean, square it, and then multiply that deviation from the mean by that group's frequency. Okay? So that would look something like, take that satisfaction rating for the lowest bin, 37, subtract the mean of, we had from the previous slide, 43. So 37 minus 43 is -6. Square that, I get 36. Multiply it by the frequency for that group, which was 4. I get 144. Write that number down. Go to the next group. That midpoint was 40. Subtract the mean of 43. I get -3. Square it. I get 9. Multiply it by the frequency that that deviation from the mean kind of represents, how many people that represents. So 9 times 15, 935. Write that number down. I then go through and I do that for every single observation. Once I have all those deviations from the mean squared, multiplied by their frequency or multiplied by their weight, and then add them all up, I get 522. Okay? So that's going to be the numerator for my weighted variance. I then still need to divide by n-1, which we said really procedure how I have to do this is the sum of the frequencies minus 1. So I add up my frequencies of add up all these frequencies, I get 65. So now it's just a matter of taking that numerator and dividing it by 65, right? No, not 65. Yeah, the sum of the frequencies minus 1 here because we've got sample data. So I'm actually dividing 522 by 64, and then I got my weighted variance. Okay. Any questions? Yeah.
Can you just say that one more time? So like you take 37 minus 43 and then square it, and then what?
And then once I have that, so that's how we have been doing the regular variance. Now that it's a weighted variance, we take that deviation squared and multiply it by the frequencies of that group. Yeah. So multiply by 4 there. And the reason why is, I was just about to go through that. So notice this bin, the midpoint's 43. 43 minus the mean of 43 is 0. This group, right, was evidence that there was no variation in the data, right? And it represented a lot of people, right? But because that deviation from the mean was 0, it adds nothing to the variance because it was observation that represented there's no variation in the data. Now, it's a little bit more interesting is a value like 37 was pretty far away from that mean, right? But it only represented 4 people. So when I took that deviation from the mean squared, and multiplied by 4, I added 144 to that variance, right? That was an observation that represented, yeah, there's some variation from the mean in this data, but it didn't become a really large number because it only represented 4 people. In fact, I could take a value that was just as far away from the mean, 49 here. It's the same distance from 43, just on the other side, but if I have 6 or -6 and I square it, it's still 36, right? But notice that deviation squared only represents 2 people. So the amount that it adds to the variance is significantly less, actually half as much, right? Because it represents half as many people. Okay? So by using these frequencies as our weight, what we're really saying is obviously some of these bins represent there's more variation in the data than others. But if they don't represent that many people, then it shouldn't really be adding that high of a value to our variance. The variance is still, the weighted variance, sorry, is still going to be a measure of the average deviation from that middle point of the data, right? Or the average deviation squared. It's just that different deviations, right, represent a much higher number of individuals than others. Okay. Any other questions on that? If something changed or... Okay. So that's our weighted variance. The next thing we're going to do, and this was, I don't think I'm getting everything mixed up, and I think I checked this before class. I didn't give you, or I gave you guys a pre-class video for today, right? I'm seeing people shake their heads. I didn't want to say it and have it not be true, but I said, yeah, I think I did. So sometimes I'll ask real specific questions. Sometimes I won't ask ICLUDA questions on it. We'll kind of see today. I end up asking you an ICLUDA question. They're probably easier to work through if you watch a video, but I'll go through some stuff before, so it's not necessarily crucial, right? But I will go through this a little bit quicker, so watching that has been beneficial. You can also always go back and kind of review that. More often than nowadays, I probably will start with some ICLUDA questions. The sections have just gotten a little off because of well, you guys are going to be missing Monday, so they're going to have like a little bit extra time this week. So I didn't kind of use it this week. Or I didn't directly use it. So what that video was going over was percentiles. So, I mean, if you've taken, you don't have to anymore. I used to assume that all of you have seen it, but now I guess you don't technically have to take the ACT or SAT, right? But if you did, or you've taken another type of standardized test, maybe ISTEP, and you've gotten your results, it tells you what percentile you're in, right? So if someone had to tell me, like, if I was in the 90th percentile, what does that really mean? And my score was, yeah, it was high, but more specifically, close. So this is actually where it gets a little bit tricky once we look at a formula. Being in the 90th percentile means that value is better than 90% of the other scores. And the reason why you're thinking, because you're probably, okay, if we had 100 people and I was the 90th, I'd be, but what it's saying is it's not that that observation is better, it's saying that value would be better than 90% of the observations, okay? Which also tells you that that value or that test score would be worse than 10% of the other test scores, right? So it's telling us that that value is better than whatever percentile we're interested in. I was using 90th as the example. So whatever percentile you want, you're saying that value is better than that percent of the data. And then it's lower, I shouldn't say better. Test scores, I guess you could say better, but right, it's higher than, and then it's less than 100 minus that percentile of the other data. So I'm in the 90th percentile, 100 minus 90, right? I'm worse than 10% of the other test scores. So I think we've probably heard of percentiles talked about. I mean, I think this is like, this is not the most widely like academic thing ever, right? People talk about percentiles, I think, in everyday life. So, you know, you see them at the doctor's office when you're young, right? This is always like the crazy, there's just so much going on here. But right, we've got inches here on the y-axis, age, and then they map out the percentile. So if I'm 13 and I'm about 5 foot here, I'm in the 25th percentile. Okay? So how are they getting these values? Like, how would they know this? Right? So the way that you're going to determine these values, even if you didn't have population data, if you have population data, it's a little bit easier to think about, like, yeah, just line people up and like figure out. But if you only had sample data, you want a value from that sample that you could then, use to make inferences about the population. Okay. So first thing we're going to do is arrange people smallest to largest. Or arrange the observations. Right. If we're thinking about this as like human height, kind of your idea of like if I had 100 people, I just line them up from shortest to tallest. And I'd go to that 90th person and say, it's like the 90th percentile. The problem is, well, instead of 100, let's use 10 people to really make this point. If I have 10 people, I line them up smallest to the tallest, right? And then I go, okay, what's the 90th percentile? Oh, it's the person in the 9th position. The problem is when I pull that person out, I don't have 10 people left anymore. I only have 9, right? So the formula that we then have to find the position that the percentile we're interested in is we'll take our number of observations and add 1 to it. So that's kind of like when I'm pulling out that one observation, I'm trying to think, okay, I have to put one back in there. So, you know, it's not going to be exactly the 9th position, it's going to be a little bit off. So that kind of this n plus 1 captures that. You'll then take n plus 1 and multiply that by whatever percentile you want, divided by 100. Okay? So in my example, if we had 10 people and you wanted the 90th percentile, we would have what? 10 plus 1 times 90 over 100. So what, 9.1? Am I doing this math correctly? No, I'm not. All right. The 9/10 of 11. So 9.9. Right? So it's not quite right an integer value. Now sometimes it works out nice, and if you have the right sample size and want the right percentile, you actually end up with an integer. So if this instead, if it had been 10, well, my life's really easy. I've got the data arranged already. I just go to the person in the 10th position, and that's the value that gives me the 90th percentile. Right? But if it's not an integer, we have to do this thing called interpolation. So I'll walk you through how we do interpolation and kind of give you somewhat of a, not a textbook definition of how to think about it. So to do this, I'm going to give an example. We have some numbers, so it makes it a little bit easier to visualize. So let's say I've got, I don't know, these metal funds, and this is how much they're worth. I just wanted a nice, easy, small data set. So I arrange them from smallest to largest, right? And the only kind of, one thing that can get tricky here, like on a connect homework or something, is remember that negative values, the larger the negative value is actually smaller. So you have to arrange it from smallest to largest. So negative 56, negative 7, 8, so on and so forth. I've got 10 observations here, right? So my n, more general form of the equation that we had was, I know I asked you a question. I'm sure I saved them. N plus 1 times whatever percentile we want over 100. So for us, the position that's going to give us the 25th percentile, which is what we're looking for here, we 10 plus 1, minus 25 over 100. That's going to tell us what position the 25th, that's going to tell us the position that has the value that would be the 25th percentile. So we go ahead and do that, we get 2.75. Well, it's not an integer, so this is a problem, right? I don't have a 2.75th position. I have a second position, I have a third position, but I don't have anything in between, right? It doesn't even make sense. So I've got 2.75. I'll look at the value in the second position, and I look at the value in the third position. What I can't do is simply take the average of the two, because the position that would have given me, if it existed, like in between, would have been the 2.75th position. So I'm a little bit closer to the third position's value than I am to the second position's value. So the idea of interpolation is if I'm in between 2 points, but I don't have anything in between, right? I don't have any numbers in between the second and third position. I don't want to simply take the average. I want to weight the value that I'm a little bit closer to by a little bit more. So what are my weights going to be? Well, if I look at whatever location I come up with using this formula, I'll use that to identify my weights. So here, I look at the decimal. That's going to be my first weight. My second weight will be whatever gets me to 1. I'll kind of give you a little bit of idea as to why in just a second. So here, that would be what? 0.25. So these are my two weights, right? Now, how am I going to use them? Well, I know that the value that gives me the 25th percentile, right, the 25th percentile value, is somewhere in between the second position's value and the third's, right? Somewhere between -7 and 8. But because I get 2.75, I know it's a little bit closer to the value in the third position, so it should be a little bit closer to 8, right? How can I ensure that? Well, I'll take the value in the third position, multiply it by my higher weight, and then add to that the value in the second position multiplied by the lower weight. We're essentially finding a weighted mean of these two values, right? So I'll take my first weight. I'm closer to the third position, so I'll multiply the value in the third position by that higher weight. I'll then add to that the smaller weight multiplied by the value in the position that I'm a little bit further from. A little bit further from that second position, so the negative 7.34 gets multiplied by that smaller weight. Questions on that? Might have to be, it might doesn't. There's no reason why it might be particularly clear. So if you have a question, it's not a not a stretch of the imagination. Okay, so we identified our weights. We then multiplied the value in the position we were closer to by that higher weight, and the one we were further from by the smaller weight. Now, one thing I'll point out here is, if we think about this as a weighted mean, these were our weights, then if we divided by the sum of our weights, you might say, well, why didn't we divide by the sum of the weights? Well, actually, technically, we kind of are behind the scenes, but because of it, when we're doing interpolation, our two weights will always add up to 1. This denominator is always going to be 1 divided by 1, doesn't change anything. So we essentially can ignore that denominator, even though it is kind of floating around in the background, right? It's just that because we're choosing our weights so that they add up to 1, that almost makes it a little bit easier for us. Any questions on this? So if we go ahead and plug these values in, we end up with the value that would be the 25th percentile is 4.23, which makes sense, right? It's going to be between -7 and 8, but it's going to be closer to 8 than it would be to -7. All right, there's no more question on. I forgot to let me. I closed this down earlier. I'll give you guys about 4 minutes to kind of work through this one on your own. Talk to the people next to you. Work on, feel free to work on these together. If I can get this to start for us here. There we go. I always keep it on AA, just as a reminder. Don't read into that or anything. It's not like I have a problem, but so that was a great job. So I'll leave this open for about 4 minutes. What I want you to find using the same data set is the value that would give me the 75th percentile. Right? So we'll use that formula to find what the position is that would give me the value of the 75th percentile. It's likely we're going to have to do some interpolation. So go to the 4-minute mark, talk to the people around you, work with people, and then we'll kind of go over it together. Yeah, don't feel like you got to be quiet. I'm not. Remember, once we had that position, the way we identified our weights was whatever the decimal was, and then the other weight was whatever got us back up to 1. Go for another 30 seconds or so here. All right. If you haven't gotten an answer in, take your best guess. And I'll kind of go over it. So 23 of us here today. 26. Everybody got an answer in that wants to get an answer in? All right, I'm gonna close it out. Get in yet? Everybody good? All right, closing it out. All right, so hey, when you work through more of these, probably become a little more apparent, having a calculator with you here is going to be helpful. But hopefully everyone could at least get the first part right. So like, probably if I look at these options, probably actually, if I was listening to what I was working through, conceptually could have figured out the right answer. Right? So the first thing we're going to do is, we've got the same kind of setup, but now what do we want? Instead of the 75th, instead of the 25th, we want the 75th, right? So what, hopefully, did anyone get, what position should we be looking for? So nobody got the position either? Right. So 8.25, right? So we want the 8.25th position. Well, that doesn't exist. We have an 8th and a 9th position. So we're going to have to do some interpolation, right? Now, if I conceptually think about what I'm doing here, before I like dive into the formula and I get too frustrated, I'm going to, the value I want, the 75th percentile, is going to be somewhere in between the values of the 8th and 9th position. So it's going to be somewhere in between 43 and 59. So right away, I mean, hopefully nobody will see up there, right? So we're in between the 43rd and the 59th. Or sorry, we're in between the values of 43 and 59. So the other ones, I guess, kind of makes sense until we remember that we're actually a little bit closer to what position? 8.25, so we should be closer to the value in the 8th position, right? This one was kind of reversed from the previous example, right? There we had 0.75, so we're closer to the higher integer. With 0.25, we're closer to the lower integer. So I look up here and I say, okay, so the value that I end up getting is somewhere between 43 and 59, but it should be closer to 43 than it is to 59, right? Well, if I look at these, right, 55 is actually closer to 59. So that one doesn't make sense. If I look at 51, I believe if I work this out, this is actually smack dab in the middle. That doesn't make any sense. The only value here that's in between 43 and 59, that's closer to 43, is 47.7. I didn't even have to do the rest of the work if I just conceptually thought about what I was doing with this interpolation. Okay? But, right, we can actually go through and do this. And it's going to look a little bit different than what we did before because we now have kind of a smaller decimal. So what will my two weights be here? Yeah, 0.25 and actually end up being the same weight as we had before. But notice now when I have like something that's less than 0.5, it's not that when I write these weights down, I keep them in that order. I have a little bit of thinking to do at this point. I identified my two weights, but now I need to figure out which value gets multiplied by 0.25 and which value gets multiplied by the higher weight of 0.75. Well, the value that should get multiplied by the higher weight is the value in the position that I'm closer to. We already said I'm closer to the value in the 8th position. So this 43.79, that's what should be getting multiplied by that higher weight, because I know that I'm closer to that value. And then the value that I'm further from is the value in the 9th position here. So 59.45. So that 59.45 will get multiplied by the smaller weight. Yeah.
So the only question I had is, like, I found the, like, 8.5, I needed 2.425.75. But how did you know that you're supposed to pick the values for, like, the values between 8 and 9? So I wasn't, like, I didn't know which values to multiply 0.5.
Oh, so what this formula is telling us is it's the position that would contain the value that would be the 75th percentile. So if I just had an 8 here, what this formula is telling me is that the value in the 8th position would be giving me the 75th percentile. So the 75th percentile value would be 43.79. Well, was it 8? It was 8.25. That position doesn't exist, but that's because we have, the position is going to be an integer, and that's why we have to do the interpolation.
Okay, because I confused that with the value. So I was doing 3 and 4, and I got like 22. I mean, it wasn't
3 and 4. Oh, were you?
Yeah, because I took that 8.25.
Oh, so you were using this as like
as the value to the position.
Yeah. So what that formula gives you is the position that the percentile, the position that would give you the value of the percentile you're interested. Yeah. That's like that's the first time. I mean, the whole reason why I did these base points like this is not going to get them all right. You're paying 100% attention, right? You get this wrong, you still get 9 out of 10 for the day. Over the course of the semester, there'll be plenty of days when I'm nice and just give you everybody 10 out of 10. So it, effort points. Do you have a question?
Oh yeah, I mean just to double check. So say if the number is like a 7.75 or something like that, we'd be looking between 7 and 8, right?
Yep. And what if we had so what if this was instead 5.9? What would our weights be? So so careful, you're in between the 5th and 6th position, but the weights that you would need to use would be 0.9, 0.1. You're closer to the 6th position, so the value that gets multiplied by the higher weight is going to be the value in the position you're closer to. So we go to that 6th position, 34.3. So the value of 34.3 is weighted a little bit higher, right? And then the value of it's in the 5th position, which is what? 33.35. That will get multiplied by the lower. Yeah. Yeah, what was 5.5? What would my weights be? 0.5 and 0.5. So each one's weighted equally. So what am I really doing there? Yeah, I'm multiplying each by a half, which I could then rewrite as just being divided by 2. I'm finding the mean in 2 numbers. So if you get a 5.5, you'd actually would just take 33.35, 34.3, find the average, find the mean. Actually, it's easy. We hope we get 0.5 or we get an integer. Those are the easiest situations, yeah. But it is a little different. That's like the good, that you're thinking about that. Any other questions on this one? So I think if we work this out, we do end up getting that 47.7, but just even the intuition behind before we got to the formula, right? And I'll do that on exams and stuff sometimes. Like if you understand the concept, sometimes you can rule things out to where you actually don't even have to enter a single value into your calculator, right? Because honestly, at the end of the day, most of this is like, we'll develop tools throughout the semester to black box a lot of this stuff using computer programs. But if you put something in the computer program wrong, it spits an answer out at you that's wildly inaccurate. If you have no idea about what a percentile or what a variance is, and you get a negative value for the variance, and you're like, yep, this is the variance. And someone's like, just because the computer told you? Like we know the variance can't be negative. Like we have to be able to understand these principles. So, all right. Any questions on this before we move on? Okay, so we're going to talk about some of these percentiles, and then we'll kind of move on to the next thing. So with these percentiles, something you might see in other courses, and I want to bring it up here. I'm not necessarily incredibly interested in it, but I know that it's used in like marketing, and even if you like, I don't know, maybe some of you are doing a dual major with some type of what we call like the hard sciences like physics, biology. you might see what they call a box and whisker plot, right? So how are they coming up with this box and whisker plot? What are maybe some uses of it? So what we'll do basically is create this box where we put the third quartile and the first quartile. Right? We kind of plot them on the y-axis. You can do it as a horizontal box and whisker plot too, but usually they're vertical. So this is simply going to be the 75th and the 25th percentile. So we'd have some data. We use this process to come up with those values that give us the 75th and 25th percentile. We then plot those to create this box. Right? So let's just, for the sake of this example, say 40 and 20. Right? Actually, I lied, 60 and 40. Right? I then find that second quartile, and let's say it's 45. I draw a line in the box kind of where that would be at on my y-axis. Now that second quartile, that 50th percentile, well, think about what the 50th percentile is. That means it's the value that's greater than 50% of the other observations, but it's also less than 50% of the other observations. That was the definition of our median. So the second quartile, or the median, is really telling you the 50th percentile. Okay? So once we plot those, right, won't go too much into it. I'm never going to ask you like to decipher a box and whisker plot. But right, if notice here, my median is a little closer to that first quartile than it is to the third. So it's kind of like I have like a long right tail. It's kind of like this long right tail idea, right? I've got a little bit of a skew distribution. I'm not going to ask you about that, but just bringing it up. The next thing we do is we create this lower and upper limit. So the way we do that is we create what we call this interquartile range, which is the difference between our third and our first quartile. So for us here, we would do 60 minus 40, and our interquartile range will be 20. We'll then take that interquartile range, multiply it by 1.5. We'll add it to that third quartile to get an upper limit and subtract it from the first quartile to get a lower limit. So what we're going to do here is draw my first whisker, which down here, this is going to be my lower limit, right? Which is just going to be what? That first quartile value. I'm going to start there. And then I'm going to go 1.5 times that interquartile range below it. Okay? So my interquartile range was 20, 1.5 times 20. What? It's 40 minus 30 or 10. So I kind of plot that lower limit of 10. Also, if I ever write anything down here and you can't see it, let me know. I wish I could, like, I don't know. These things I think are worthless anyways. But yeah, make sure you ask. Okay? I then do the same thing to get my upper limit, right? But now I start at my third quartile and add 1.5 times my interquartile range of 20. All right, so 1.5 times 20 is 30. And I get this upper limit of 90, right? That's my second whisker. Okay? So I've got my box and my whiskers plotted now. What the hell do I do with this thing? Right? Well, what this does is say, well, look, here's the majority of the data in between this first and third quartile. Right? If I go, take that range and then, multiply it, make it even larger, multiply by 1.5, and I go below the first, above the third quartile, this is going to set a range that I say, look, anything outside this range, it's so wildly different from the rest of the data, something has to be wrong with it. Like, it's probably a bad data point. So you see these used a lot more in science because it's like in clinical trials and things where it's like, well, most people's responses were here, but we had this one person who, like, my brother's does exercise, like kinesiology, exercise science, and they're always looking at like, sometimes I'll look at like muscle growth response or something, and like, or even like weight gain, like you're trying to talk about like different diets and things. It's like, oh, most people like, gain 5 pounds, 6 pounds, some 10, maybe there's a couple, 1 or 2, some people lost a little. And then they had one person who gained like 70 pounds. You're like, okay, well, this is clearly an outlier. This wasn't a result of whatever we're running the clinical trial on, but we need a justification for getting rid of that data point. You can't just throw out data that you don't like, right? So when we set this lower and upper limit, we're not going to say, okay, if we have an observation that using all the data to create this box and whisker plot, and upper and lower limits, if I see any data points above the upper limit or below the lower limit, I can justify getting rid of those because they fall outside of this lower upper limit range, right? Which is kind of useful if you have these really, extreme values that could greatly skew your data, right? So this is called the Q test. If you ever have a point that falls outside kind of your whiskers, you can say, we identify that as an outlier. Here's justification. It's outside the lower upper limit. We can actually exclude it from our data set moving forward. So it doesn't skew or it doesn't mess up any of our other statistics. So don't reject me as an outlier because you were the Q test. And this is, I thought this was a great thing. I didn't even make this one. It was already floating around up there somewhere. So you might see that in other classes. I won't do much with it other than like knowing how to calculate those percentiles. It's something that is useful, not only for creating box and whisker plot, but just more general. So what we're going to end today on, I will pick up on it next week. It's going to be a somewhat long discussion, probably. I don't think we'll finish today. I'd be surprised if we did. Is kind of like where we're going through distribution stuff early, and then we were like, well, we've only been looking at one variable. Like maybe we care about the relationship between variables. So we created these scatter plots, right? And those told us something about the relationship between two variables. Well, now we've been coming up with all these descriptive statistics for one variable. Well, maybe we want some statistics for understanding the relationship between two variables. Right? So, let's, I'll call them X and Y, and I might give some toy examples at the end, but let's say we have two variables, X and Y. If X goes up, the other variable can go up, it can go down, it can not change, right? And three different outcomes. Okay? So we're gonna have two measures of whether or not as X goes up, does Y go up, or X go up, does Y go down. We're going to call those the covariance and then the correlation or correlation coefficient. So the first one we're going to talk about is the covariance. Right? So the way we write this covariance between any two variables. So right now I'm calling them X and Y. This could be height and weight, years of education and income. Right? We're going to use this sigma, which usually would represent a standard deviation. Right? But because we're writing two variables on the subscript, that changes that sigma to representing a covariance. So it's the covariance between this X and Y variable. So to kind of break this formula down, the process of what we're going to do, and I've got a sample data set in a second. We're going to take that X variable, calculate its mean, take the Y variable, calculate its mean. I'll then look at each observation. I'll take that observation's X value, its deviation from the mean, and then multiply that by that observation's Y value's deviation from the mean. So once I do that for every single observation, I'll then add them all up and then divide by the total number of observations that I have. So I'll talk a little bit more in a second. I think I'll show you some data that'll make a little more sense. Well, we also have a sample covariance, same exact idea. Just like the variance though, now instead of dividing by n, we divide by n minus 1. Not a whole lot different than the variance. So what does the covariance actually mean? So if I end up with, after I calculate this, a positive value, I'm going to say that there's a positive relationship between X and Y. As X goes up, Y tends to go up as well. If it's negative, that's telling me that as X goes up, Y tends to go down. Right? They move in opposite directions. And if it's like pretty much 0, that says as X goes up, Y doesn't really change. So there's really no relationship. Those are kind of our three different categories. Right? So we're really looking at the sign of this covariance. Okay? Now I'm going to show you this data set because I think it helps me helps me a lot. Or what? I can't talk about it. It allows me to describe this in a way that's going to make a little bit more sense to you. Okay? So we've got this numerator, and that's really capturing the relationship between the X and the Y value, right? This whole dividing by n thing, that's just because it's like the same idea with the variance and the mean. We're really just weighting each one of these observations by 1 over n. But what that numerator is going to do is it's going to go through. And if you have an observation, so let's say I calculate the means here, right? I've got height and weight. I want the covariance of height and weight. The average height is about 64 inches in this data set. The average weight is 187. So I look at this very first person. I say, okay, they are above average height, right? If I took that person's X value and subtracted the mean, that difference, right? 70 minus 63 is going to be a positive value. They're above average height. However, when I look at this person's weight and I subtract the mean, they were below average weight. And that was the second part of that covariance equation. So I've got their deviation from the average height, deviation from the average weight, and then multiply those two together. And what that tells me is, well, if observations are on the same side, if observations have values for both variables that are on the same side of the mean, that's going to add a positive value to the numerator. If I have an observation where its two variables were on different sides of the mean, that's going to add a negative value to my numerator. I'll explain why a little more in a second. Notice here, this person was above average height, but below average weight. This one person was evidence that these two variables tend to be on different sides of the mean, right? Or that when one is higher, the other is lower. Now, intuitively, we know the overall relationship between height and weight probably isn't negative, but this one person provided evidence that those two variables tend to be on the opposite sides of the average. So it's adding a negative value to that numerator. It was evidence that these two variables tend to be on opposite sides. Right? And if they're on opposite sides, we're going to end up with a positive times negative that adds a negative value. However, let's look at person 3 here. This person was below average height and well below the average weight. Right? So when we look at their deviation from the means, they were below average height and below average weight. So they were evidence that these two variables tend to be on the same side of the average. That when X is low, Y tends to be low as well. Well, even if it's that they're both below the average, a negative times a negative ends up being a positive, right? And if I had an observation where the height and weight were both above the average, I'd have a positive times a positive, which would be a positive. So whenever I have observations that have values that are on the same side of the average for these two variables, those were observations that provided me evidence that there was a positive relationship between these two. That they both tended to either be above the average or they both tended to be below the average for both variables. Okay? Any questions over that idea or concept? I want someone to clarify a little more on that. So that's what that numerator is capturing. Now we're doing this for every observation. Like I said, this first person that's above average height, below average weight, we probably know if you had to tell me, what do you think the covariance between height and weight probably is? As height goes up, what do you think probably tends to happen to weight on average? Probably tends to be a little bit higher as well, right? There's probably, we probably think ahead of time there's a positive relationship. But this one person was evidence that there's actually a negative relationship. And that can be true. Like the average, we look at all data, the average covariance can be positive, but for any one person, right, they might not have the average effect, or they might not apply to them. But what we're going to do is look at across all the observations, what was the average relationship between these two variables. So we're going to add up those products, right, the deviations from the means, that product. We're going to add that up for every single observation, and then divide by n-1 if we have sample data, which here I have what? 44,000, so 44,000 minus 1. Right? Once I add all those up, I did that and I get about 76. So the covariance is kind of telling us the average relationship between these X and Y variables. They tend to be on the same side of the average or on different sides. The problem is, what 76 what? Right? What does this tell me? Well, it tells me that they're tend to be on the same side of the average, but I don't know, how strong is this? Like, should I be seeing something in the thousands? Is this typically only around 10 and 76 is actually high? Well, it all depends on what variables we have. So unlike the variance, right, or the mean, right, our units get real goofy on a covariance because let's say I was doing height and weight and I've got inches times pounds. The units of my covariance is going to be inch pounds. I don't know what the hell that is. Right? Like, what good is that, right? And I can't compare across data sets because if I had years of education and income, I'd have years times dollars. What's a year dollar, right? So the units make the covariance kind of useless, right? And then I can't compare, so I can't compare across different types of relationships. Right? Now, I guess I could compare within the same type of variables. Like I could look at the covariance between years of education and income in the US and compare it to the covariance for years of education and income in China, right? And I could then say whichever one's larger, there's a stronger positive relationship in the US, maybe there's a stronger positive relationship in China, depending on the size. But I can never compare like the relationship of years of education and income to height and weight, right? Because they have completely different units. So we have a solution, right? How can I compare across different relationships? So we're going to calculate this thing called the correlation coefficient, which uses the covariance, right? It basically takes the covariance and says, look, I realize this is not a very useful statistic, right? In comparing relationships, but I can scale it, okay? So the population correlation coefficient, we're going to use what? Rho, and then the sample, we're going to use R. All we're doing is taking our covariance and dividing it by the standard deviation of each variable. Okay? I'll show you mathematically a little bit of support about why this helps scale it. But the idea is that if I'm looking at a variable like height, there's a lot less just, even if I think about the range, even if I don't want to think about the standard deviation yet, the range I see for height might go from, I don't even know, the shortest person to the tallest person. I can't imagine it's going to be any more than like 40 inches, right? Or maybe more than 40, 50, 60 inches. Right? That's like what, 5 feet? So the tallest person in the world was like 9 feet, I think, at one point. Some 4 foot. Yeah, so we're like, not a very big range. But if I'm looking at income, hell, income is going to go from 0 to the millions, right? So even the range, like I know that there's just more variation in that income variable than there is going to be in that height variable. So I want to account for that. So when I divide by this standard deviation of each variable, it's almost like I'm taking that covariance and saying, look, the covariance was kind of dependent on how much variation just existed in the original variables to begin with. So if I divide by the standard deviation here, I'm going to account for that, right? I'm going to scale everything down so that it has the exact same amount of variation, or if you want to think about the same range that it could take on, okay? So our correlation coefficient is always going to be between 1 and -1. When we divide by the standard deviation of each variable, that covariance by the standard deviation of each variable, we end up with a measure, this correlation coefficient, that will be between 1 and -1. 1 represents the strongest positive relationship you could ever see between two variables. -1 represents the strongest negative relationship you could ever see between two variables. Okay? So the reason why this scales it, to give you kind of an idea behind why. So I'll do the population covariance to show you this. So the population covariance would be what? The sum of the observation's deviation from that X variable's mean times the observation's deviation from that Y variable's mean. And then we divide by whole number of observations. And I decided we're doing population, so I should be actually writing this as mu for the X variable, mu for the Y variable mean. I'm then going to divide that by my standard deviations. So the standard deviation is going to be the square root of what? The standard deviation for X is just adding up every observation's deviation from the mean squared, divide by n, and then the standard deviation for my Y variable, exact same thing, but right, we're looking at that deviation from the mean for the Y variable. I'm just writing out, plugging in my equations I have for the covariance and the standard deviation. Well, you can, and this is by no means is this like an accurate mathematical proof. It's more of like a intuitive. You can kind of see where I'm going. It's not step by step for all this mathematically. So don't show this to anybody in the math department. But you can kind of see the idea here. Like I'm taking the square root of things that are getting squared. So you can kind of see how that's going to cancel. And then the square root of n times the square root of n would just be n. So I'd be dividing both the numerator and denominator by the same thing. So those actually cancel. Well, now I've got like the sum of my deviations from for x from its mean times the sum of the deviations from the y. It's not quite the same thing as my numerator, right? Because this is like all within the sum. So you kind of feel that these things will kind of cancel a little bit as well. And that's why at most, you're only ever going to see one or negative one. More likely than not, you're going to see something in between. So like I said, this isn't like a perfect mathematical proof. You can kind of see like there's a lot of things that are really similar that are going to cancel. And that's because when we divide by standard deviation, we're really just scaling. We're kind of accounting for the original variation in both these observations. Okay? So now I could compare something. So we could do this for the CDC data, right? I could plug in my covariance, plug in my standard deviations, right? And come up with that correlation coefficient. So scaling that covariance that we had of 76 that wasn't useful, the correlation coefficient is 0.45. Is that the strongest relationship? Is it the weakest? Well, I mean, the strongest would be 1. The weakest is 0. So it's somewhere in between, right? There's no like rule of thumb for what a quote unquote strong relationship would be, but we can compare across data sets now, right? So maybe I have this covariance between height and weight is 0.45. And I might want to say, okay, how does that compare to the relationship between test scores and the hours of Netflix watch, right? So I've got height and weight is going to be a correlation coefficient of 0.45. Maybe I want this correlation between, we'll do test scores. And so test scores times and Netflix, right? We've got test scores and Netflix that we're interested in. So here we're going to assume that the correlation between the hours of Netflix watching your test score is actually negative, right? And if I told you it's a stronger negative relationship than the positive relationship that exists for height and weight, then you know that this correlation coefficient has to be somewhere within what range? So I'm telling you it's a stronger negative relationship than what we found for height and weight.
0.46 to -1.
Basically anything above 0.45, but we know that it's capped at 1, right? And so now we can compare across relationships. Okay? So, really what we're trying to get at is when I was talking about scatter plots and the line of best fit, that slope of that line, you can kind of think about that's a correlation coefficient. Right? It's kind of telling you the relationship between this X and Y variable. I'm not going to kind of make you do this one, but if you want to, plug these numbers in, this is pretty easy, right? But as long as I gave you the covariance and I gave you standard deviations, it should be pretty easy to find the correlation coefficient. But first of all, in this one, what answers can we rule out right away? Well, B makes no sense, right? It's way outside the range of -1 to 1. But what's the other one we can rule out? D, why? Yeah, when we think about the correlation coefficient, let's see if I have the equation. I have it here, right? The denominator is always positive. Standard deviations are always positive. So the sign of my covariance tells me the sign of my correlation coefficient. So because my covariance is positive, I know that the correlation coefficient can't be negative. Right? So I could rule that one. And I had another question in here that was related to a video I want to show you. Maybe I'll say this at the end of class on Monday, right? So we don't meet until Monday. So I'll save this until maybe Monday, and then we'll start jumping into probability. But at Learn Smart, you don't have to kind of watch that until before Wednesday's class, and we'll really be getting into like some heavier probability issues. Okay. All right. We'll see you guys on Monday.